I am Sanja. I actually no longer NVIDIA. I just announced it yesterday, recently left. But NVIDIA has been really kind and actually allowed me to take my slide deck with me, or at least quite a lot of the materials. So I'll be talking about the NVIDIA work today. But today I'm a civilian at University of Toronto, and I'll let you speculate about my next steps. All right, so not really going to talk about agentic AI today, but I'm going to talk about world models, which is really something very exciting to me, really for the last 6 years. But now this technology is maturing, is around the corner. All right, so we've been working on physical AI for quite a few years, and the world has been working on robots for decades, right? But if you look at kind of this evolution of AI, ChatGPT 2022, kind of the entire world knew about AI. It was the first time that really reached the masses. My mom knew about ChatGPT, right? Right now, we are in the era of agentic AI. Everyone is using agents. I don't need to explain what it is. I cannot imagine my life, actually, without using agents. And the next breakpoint that is coming, perhaps in the next decade, maybe more, depending on the kind of robot we're going to looking for, is physical AI, where all this intelligence comes to the edge, comes to the robots, in many different roles, in many different industries. All right, so at NVIDIA, we were currently, my group was more focused on one particular robot, that was autonomous driving robots. Today, we're going to kind of use that as an example. But obviously, there's many robots, especially general robotics is kind of the hot field that's upcoming, and it's the robot that's kind of, a lot of echo, supposed to do many different tasks. Okay, so the evolution of kind of the software to deploy on smart robots, for example, a car, kind of went through different generations. From very simple AI, very simple vision, to more hard coding rules around how could I be driving around, to machine learning in every single steps, both in perception, but then also prediction and planning and how I'm going to actually drive the car. To most recently end-to-end systems, where I'm just taking sensor data and outcomes, basically a planning trajectory that drives the robot, drives the car, to perhaps the new generation that's coming, which is leveraging this big foundation model pre-trained on massive amount of data that come with this vast knowledge about how the world works around all the corner cases that is so hard to collect in the real world, and also know how to reason. So people really think kind of these foundation models are a game changer to really kind of that last mile to solve the corner case in robotics or in AV as a first complex example. All right, today I'm not really going to talk about so much about the software that goes on the robot, but about the infrastructure, particularly simulation, right? So if you think about LLMs, during development, people train a lot of different models, and you need to somehow evaluate how good they are, which means sampling from the model, get some text, and have some way of evaluating how good it is. Sometimes even interact with a human, right, if you want to measure conversation. So something like that in robotics actually needs to be deployed on a real robot in closed loop, right? Meaning I have a software, the brain of the robot, I deploy it on a real robot, this robot starts performing some tasks. Here I have some video from Skilled AI that I pulled from the internet. Real robot doing pick and place, running this policy, which we develop in our environment. And then, the human is kind of observing how good this robot is doing, right? An alternative is to actually have a robot do this in an entirely virtual world, right, on the cloud. So it's a virtual robot in a digital twin, also doing pick and place, right? And we can also evaluate how this virtual robot is doing, and that can also give us a really good signal about which policy that we develop is actually better, right? And we can also train that way much more scalably. So if we look on the left side, the development is kind of bounded by deploying on the robot, which runs with physical time. We cannot, in the real world, we cannot run faster than the physical time, right? So if we want to scale and evaluate many different scenarios, we need to buy many different robots. On the cloud, on the other hand, we're bounded by compute time. Computers are getting better and better. We can actually run faster than real time, and we just scale across GPUs, right, instead of robots. So it's a much more scalable pipeline. So simulation is really kind of foundational infrastructure for robotics. I really don't think you can develop robotics without really, really good simulation. Let me skip this slide. And talking about simulation, it has kind of gone through different stages, right? So, traditionally this was done by graphics. Artists would carve out, create 3D assets, write behavior models, write all the ray tracing equations, and then you would get out, a particular scenario. It kind of worked, but at the same time, it was so time-consuming. If I wanted to test my car at some street in San Francisco, that goes 1 or 2 months of actually artist time to create that digital twin. Then around 2020, a new technology came along called Nerve or Gaussian splats that completely changed the game. And the game changer was that now you can go from a recording, from a real-world recording that you capture on a real robot, to a simulation environment with some restrictions because it was all done by reconstruction. So it was kind of limited with what you actually saw in that recording. But it was a game changer. Suddenly, the content problem was solved. You could go from real-world capture to a simulation environment, deploy a new version of your software, and make new closed-loop rollouts and actually test new policies in these environments. How did this work? It was all reconstruction-based. You have your capture, you get your surface reconstruction for collision checking, and then you're inferring Gaussian splats, which is this kind of little appearance blobs in space that tell you how to render different viewpoints. Complete game changer at NVIDIA. We were doing 2 million simulations per day testing autonomous driving software. All right, so is that enough, or what's coming next? Like I said, there was a lot of limitations of how you reconstruct the environment, what kind of environment you can actually handle. Plus, at the same time, it's also bounded by what you have recorded. And we talked about the robotics is going to hit the long tail, which is stuff that it's so hard to see. And you actually need to test and train in those environments. So it's all about imagining those hard cases as well. And this is where world models or generative world models come in, right? This is AI purely trained on data. It's completely data-driven. There's no more human crafting content. So the limit is the data, and we have learning LLMs. That's basically the way to go. And suddenly you can hallucinate new scenarios. You can write whatever new hard edge case you imagine, and very kind of hard dynamic scenarios. Lots of progress on this front, right? Especially in the last year. Now we can generate really crazy hard scenarios. Kind of like hard weather. No one got hurt in that video. It was completely generated accident. It's just really kind of those cases where you want to test the software. Here we can even change the viewpoint, which is similar to basically changing embodiment, going from lower car, sports car, to a truck. Super important, so you can actually test across different vehicles. And the last really important thing that's very easy to do with generative models, but a little harder with reconstruction tech, is editing. Just text prompt, and suddenly you can edit the scenario in different ways. All right, there's a specific architecture that I have in mind when I talk about world models today. And it's interactive. So it's not just I'm getting text, I'm getting out a video, 5 seconds of video. There's a user or a robotic software in the loop. Here, our favorite human at NVIDIA was actually our first user. As soon as we developed the model, we went to his office, and he was the one trying it with a real steering wheel. So in this case, it was a user driving, and every single frame that you saw was completely generated by the world model. And that's what I mean by world model in this presentation, and that's why being interactive. There's a robot or a human in the loop. And that model that we developed was called OmniDreams, and the bonus is that it runs real time. Does simulation interval real time? Not necessarily. It just needs to have really high throughput, but real time is a great bonus. All right, so I'll just do a quick glance of how we actually developed this. Today, obviously in the future, this is going to be a lot maybe simplified and so on. But right now, everyone starts with a base model. This is a pre-trained video generation model, typically based on diffusion. So you have a few, like a noisy frames, and you denoise them into, a few seconds of video. This is what I mean by bidirectional attention model. Now we typically do domain post-training. This was pre-trained, typically, a vast amount of publicly available internet data. Now you need to go to a specific robotic domain, for example, AV, and you need to post-train such suddenly I can start generating stuff that happens on the road, right? And not just stuff that happens on the road, stuff that is captured by a robot, which is typically more than just one single camera. It can be many different cameras. Then we need to train this architecture, right? We said we need to make it interactive. So we actually changed to have this causal architecture, right? So it needs to generate frame by frame, or at least like short snippets of video at a time with action in the loop. We need to make it efficient. Typically in this diffusion models, you do many steps of distillation, which makes it slow. But you need to distill it into just a few steps of distillation so you can actually be much faster. And then you do all the tricks in the book to actually have a real-time implementation. And this is Flash Dreams. We released it, and you can plug it on different architectures of world models. And then the world model comes out. So here you have someone driving. On the right side is a steering wheel that's being operated. Every single frame here is not the real world. It's completely generated by the world model. And here we have very simple physics. It's just physics on the ground. So we make sure that the car stays always on the ground, goes over speed bumps, but you can actually go through a restaurant no problem. So we didn't have collision checking on more complex part of the scene than the road. All right, I wanted to show this because I think it's really showing the trajectory of where this is going. March 2025, we were generating 5-second clips, 5 minutes or so. 5 seconds, 5 minutes of GPU time. Okay, it was clearly not practical. On the right side, March 2026, that was fast forward by 1 year, real time, interactive. Okay, so this is how fast this technology is evolving. This is why I mean it's around the corner. At CVPR, which was basically 2 months later, this was June, we even made it work on RTX 5090, which is basically a consumer-grade GPU, which is awesome. It's literally a game engine that you can have in a backpack. Just some example results. Everything here you see is completely generated, and it's just giving it a text prompt or a first frame, and you get a desired scene, which is much more complex. There's no way that this can be done by graphics engine. It's just too much, or too many different phenomena going on. And it's very hard for the construction tech to actually generate this as well. And this is basically showing what you need to do in the end, which is generate multiple different sensors that you have on the robot. This is pretty cool, because here we're actually editing the same environments. We can change the weather, the lighting conditions, and that little green trajectory that you see, that's actually the robot's policy driving in this world. I was actually super excited about this result because we plugged it in the production policy, and it was driving in this world. It's confusing the simulated world with the real world, which is basically means that the quality bar is at the level that you actually need. Yeah, and I asked my guys to generate some cool examples. And this is basically just saying that you still capture that internet knowledge. So even though NVIDIA has never captured an elephant on the road, you can actually generate it, which is proving the point on that long tail. Yeah, and then maybe just kind of end here with the interactive demo. Just so that you see it actually runs real time. On the left side is the person really driving it. Every single frame is generated. On the right side, you see that wheel rotating. That's actually the robotic software operating that wheel and driving in this 3-camera world model. So thank you very much. I'll stop here.